Wow, there's a lot of information on this diagram, so let's put some order in this. What we're actually showing here is the thrust coefficient on the vertical axis, again plotted versus the axial induction factor A. And maybe we should indicate that. So here we have the thrust coefficient, and here we have the axial induction factor A. And we're doing that for all kinds of rotary wing aerodynamic flow states. What we know so far is, well, we know the parabola. We recognize the parabola for the thrust coefficient, which is the green line here. And yes, the green line turns from solid into a dashed line for axial induction factors A larger than 1/2, because we saw that in this case the exit velocity at the end of the stream tube reverses, and so because of that momentum theory is no longer valid. What happens now is actually at some point this reverse flow is reaching the rotor disc area itself, and it progressively moves towards the rotor disc area as the axial induction factor A increases. Ultimately, if the reverse flow region hits the rotor disc area, we enter the so-called vortex ring state. That's something that's very dangerous if you're flying in a helicopter, and the only way a helicopter pilot can get out of this situation is by moving the helicopter to the side or moving forward. If the axial induction factor is yet further increased, the vortex ring states turns into the propeller brake state. Everything here is highly non-linear and absolutely not something that momentum theory can help us with. So what do we do if we get into the turbulent wake state? What happens here? Well, there's a number of experiments. You see these symbols here that were conducted at NACA and BRC. And for propellers of different solidity and advance ratios or tip speed ratios, you name it. And it's kind of a shotgun approach. And what the solid blue line is showing here is sort of a curve fit. And we know the curve fit has to be tangent at some point to the solid green line where momentum theory is valid. And in the end, for an axial induction factor of A equal to 1, the thrust coefficient becomes 2, which is related to a flat plate drag coefficient. That's why that is so. Later on in this course, when we talk about the blade element momentum solution algorithm, this empirical relation that's attributed to Hermann Glauert will be further explained and be worked with. Now, wait a minute, what happens actually if the axial induction factor is 0 and becomes negative? Well, we saw the reason why a wind turbine takes energy from the main flow is because it slows down the main flow. Meaning the velocity at the rotor disc itself is equal to V0, the wind speed, times 1 minus A. So it reduces it. So now if A becomes negative, 1 minus A becomes positive. So we're actually accelerating the flow at the rotor disc. In that case, the windmill becomes a propeller. And so still in propeller theory, we also have a region where momentum theory is indeed valid. One more thing I'd like to point out here. In the windmill state, the stream tube is expanding, we know that, and the thrust is directed in the flow direction. So it's really a drag, not a thrust. This changes in the propeller state. The propeller accelerates the flow, thus the stream tube contracts and the propeller generates sort of a jet in its wake, and The result of that is that the thrust force is in the opposite direction towards the incoming airspeed. And the thrust is really a thrust. The propeller is propelling us forward, while the wind turbine, in that case, the thrust is more of a drag, and it's pulling the rotor backwards and generating a large bending moment on the tower and foundation.